2, 3, 4, 5. One, two, three, four, five. Okay, that something happened. Did I change the? Oh, pardon lah, wrong one. Right. Eh? It's be live already. Oh, right. Okay. Yes, alamak, you'll see this. Okay, test. Right, you can text me in the WhatsApp group if you have any questions. If not, I will go through some of the common things that you all have asked through the SLS. I'm supposed to remove this. Right, okay. I think one of the common things that you all actually ask is regarding the current potential difference and resistance. Okay, let's see. Isa. Oh, where you go? Isa, go there. Come, Isa. Go there. Go. Isa, go play inside the room. Okay, right. So yeah, so Isa, wire. Isa what? Isa, there's wire. Isa. Me. Okay, yes, as I was saying, yeah, some of you asking, how are these all related? Okay, let's look at current, resistance, and potential difference, not separately, but as a whole, right? How they are all actually linked together. Okay. Why are you showing question mark? It's not funny. It's really weird. Don't do this to me. Right, it should be working, right? Yes, it's working. Why are you giving me this weird stuff? Right, 9V. Oh, selenga. Okay kan? Right, that should be correct, right? Okay, right. Okay, just okay. So we have all these three. We have the energy source. We have current. We have the voltmeter here to measure the potential difference. Okay, so we see how they are all linked. Okay, first off is the source itself. Okay, the EMF. Okay, this is the one that supplies the energy. So if I adjust the voltage higher, right, you go by definition, it says voltage is the same as joules per coulomb, right? So when I increase the coulomb, wait, sorry, yeah. Okay, so when I increase the EMF, okay, I'm increase the energy that each coulomb of energy have. Okay, and EMF by definition is the amount of work done by the energy source to drive a unit charge around the complete circuit, right? So when I increase the voltage of the EMF, definitely I'm supplying more energy. So you can see that when the charges have more energy, right, they will move faster, and that has an impact on the current. If you look at the ammeter here, right, this is a low voltage. I increase the voltage, the current has increased as well, right, because current is the rate of flow of charges. Okay, so the faster the charges flow, then the higher the current will be, right? So by now I've not changed anything else. The resistance has remained the same. The only thing I've adjusted is the EMF, which has a direct impact on the current, and the other direct impact is actually also on the PD of the resistor here. Since there's only one resistor, so whatever PD there is, so whatever EMF is there, is equal to the PD of the resistor. Okay, so that is the first kind of link that you should appreciate, right? So let's reset this back to a normal level. Okay, let's say I set it back to 3V. Okay, so when I increase this to 3V, I reduce this back to 3V, right? The current is 0.3 and the EMF here is 3V as well, right? So next, what happens when I change the resistance? So resistance has a value of 10. So when I increase the resistance, Okay, look what happens to the current. The current reduces, right? So the current reduces. So resistance, right? It slows down the flow of the charges. So when you have a higher resistance, the current will decrease as a result. Okay, this is by not changing the EMF. The EMF has remained the same. If I make the resistance in the circuit higher, the current will reduce. So it has a inverse relationship, right? So increasing resistance will decrease the current, right? That goes back to our Ohm's law, like R equals to V over I. Okay, or I can link to many other different forms of the same formula, I equals to V over R, right? So when just now my voltage remains the same, but I increase the resistance, the current decreases. So this is the link between potential difference, current, and resistance, right? Okay. Okay, so if any questions at this point in time, do drop me a message or something, so I can try to reply. Okay, yes, I'm a bit slow to respond. Okay, but hi, Hafiz and Jeron. Right, thank you for tuning in. So, do ask a question, right? So that hopefully you will learn something out of this session, right? Because I have a back-to-back streaming, so let's make the best of our time, right? Okay, hey, I'm back. let me further explain how to use the proportion method to find resistance of a conductor, right? Okay, so we're gonna find the resistance of a conductor using this formula, rho L over A. Okay, so right, it's very unlikely that you'll be asked to use a calculation exactly to put in the values to find resistance. Okay, normally the common kind of questions they will ask you is to compare uh, the resistance of one conductor against another. So let's say we'll begin with having a conductor which is, let's say, of a certain length. Let's say it is 1 meter long. Then it has a, let's say, a cross-sectional area. Okay, cross-sectional area, not diameter, right? We keep it simple as a cross-sectional area. So the cross-sectional area, let's say we put it as, like, say, 2 mm, 2 mm square, 2 cm square, right? Okay, 2 cm square. Okay, and this conductor has a resistance, let's say 12 ohm. Okay, so it's live, right? Okay, it's live. Okay, so normally we'll ask you, okay, what if we give you another conductor? What if it is 2 meter long now? Okay, please find out what is the resistance of this conductor. Right, everything else is the same, right? The cross-sectional area is also 2 cm square. There's no change, right? I have inconsistent band thickness. Okay, so how do I then do such a question, right? So we can do a table method. So we divide the table into a few columns, right? So the first column will be the length. This weird thingy going on. Okay, so then length, area, and resistance, LAR. Okay, so we begin with the first first row. First row will start as a reference. So there is the original conductor given. So the length of the original conductor is 1 meter. Original cross-sectional area is 2 cm square, and the original resistance is 12 ohm. I'm having this weird effect. Okay, so then now we input the new conductor, which has a length of 2 meter, a cross-sectional area of 2 cm square. Wait, what's happening? And find the resistance, right? So we are doing the proportion method. So we take the first row as a reference. So we find out in how many times in terms of the comparison to the original is the new row. So the new row in terms of length is twice the length, right? In terms of the cross-sectional area, there is no difference, it's still times 1, right? So how do I get the resistance? So we look at these values here, the one that we just did, the times 2 and times 1. Okay, we use this to calculate. I don't know why this thing keep popping up. Okay, so resistance here is 2 times 1 times 12 ohm, right? We take the highlighted value, 2 times 1, and times the original resistance, which is 12 ohm, right? So when we do that, we find out that this has a resistance of 24 ohm. Okay, this is a very simple case scenario when only one of the variable changes, which is the length, right? So we can do the same, right? Let's say we have another question where now instead of the length, I change the what you call that, change the cross-sectional area instead. So let me give you another example. So now I make a cross-sectional area which is, let's say, twice as thick but of the same length. So now my area is 4 cm square. Okay. Did I change color? That's weird. Okay. Okay. So my new length, I use a different color, right? Your new length is 1 meter, but the cross section area now is 4 cm square. Shia, Liana, and Luis, hi, welcome to the channel. Click the subscribe button. No, just kidding. Okay, so resistance is okay. So now we find the resistance. So again, we do the same thing. Compare in terms of length is times 1. In terms of the area, it is times 2, right? But remember the formula for resistance is rho L over A. Why my handwriting is really bad today? Okay, so A is actually an inverse function, right? So when I multiply the area by 2, right? So it's actually 1 over 2, right? Because 2 is in the denominator. So 2 to 4 is actually 2 times, but because it is a reciprocal, so it becomes times 1 over 2 times. So 1 over 2. Why are you not registering? Okay, so it's times 1 over 2. So to calculate the resistance, I take 1 times half times 12. So that gives me 6 ohm. Right? Okay, so far I've only changed one variable, length or area, right? But the question may not be so kind. They may give you 2 variables that change. So what if 2 things change? This thing's like going up and down for no reason. I don't know why. Is my computer being hacked? Okay, so let's say okay, now I give myself a more challenging question where I change weird. Okay, I change, what other color can I use? Purple. Okay, where I change both area and length. So now let's say I have a smaller cross-sectional area and maybe I make the length twice as long. So now 2 meter long but 1 cm square for the cross-sectional area. So what is the resistance of this new conductor? Don't like that lah. Why you keep popping such things up? Okay, so did I write in a blind spot? Maybe I should write higher. Okay, so when I have a length which is 2 meter, cross-sectional area which is 1 cm square, what is the resistance? So now we are doing the comparison all over again. So we look at this. This is 2 times, right? This is half the time, right? Half, because the area is cross-sectional area, from 2 cm square to 1 cm square is half. So it's reciprocal of half. So it's 1 over half, right? 1 over half. What is 1 over half? 1 over half is already bigger. 1 over half is equals to 2 times, right? So my resistance will be 2 times 2 times 12. So that makes it 48 ohm. Okay? Right, so this is how we use the proportion method. Right, it's similar to something you do in math as well. Right, the concept is the same. Yes, hi Mariam. 12:27. What time is it? Oh, okay, quite recent. Hi, peace. Okay, there are 7 people watching, not bad. 6, 1 has left. Okay. Yes, any question, you can type in the comments. I will respond to you. Guys, you are pretty quiet now. It's opposite of what's happening in class. In class, you are quite chatty. Online, you are so quiet. Is that the pattern? Like, you know, classes that are quiet, they become very chatty online, and chatty classes become very quiet online. Right. Thank you for the like. Oops. Okay. Yeah, see, something's weird going on with the control. It keeps going up and down for no apparent reason. It's a glitch. I have no idea what's happening. Right. Is it my keyboard? Did I press anything? No, I did not press anything. Oh man, if no question, I hope you ask question though, right? We don't have a lot of this kind of like time together, so ask question, right? It's 12:30, maybe it's lunchtime. You all are not really asking question. Okay, maybe you'll go and have a lunch first. Think about what you wanna ask. But by then, bye bye, sayonara. I'll be gone. I have another class at 1. I have to prepare for that. It's not easy to do a live stream, I can say. The setup is pretty tedious, especially for this setup. You can see what's happening here. Okay. You all are watching, but you all are very quiet. Can you say something? So there's a slight breeze now. Nice. It's a very hot day. Drink more water, right? And my water's out. Any questions? Sorry, Chair, I haven't formed any questions yet. It's okay. Yeah. I started this live based on whatever Q&A that was given. I mean, whatever question that was posted in SLS. So I used that to start this live, right? So if anything along the way you have questions to clarify and all that, yeah, sure, go ahead, just ask. Okay. Please finish up your SLS punctually, right? Because otherwise it will just snowball into from a so I call it, from a molehill into a big mountain of homework, right? So please keep on task when it comes to your work.